I'm tempted to say you're probably sick of balancing equations by now, but I know it's really fun. Who could ever be sick of balancing equations? So one more and then we'll get to some new stuff. Zn plus HCl goes to ZnCl2 plus H2, and we want to see how many of each reactant and how much of each product we'll have and make in this reaction. So I'm going to start out, I'm going to write Zn, H, and Cl over on the left. See exactly how many of each one we have, and Zn, H, and Cl over on the right, and we'll figure out how many we have over there too. Just as the equation's written, I see one Zn, I see one H, and I see one Cl on the left. And on the right, I see one Zn, I see now two H's, and I see two of the Cl's. So now we just want to go and figure out how we can change this thing. Right now I see the Zn's are already balanced as of now, but the H's are unbalanced, the Cl's are unbalanced. It doesn't really matter which one I start with because the H and the Cl are together in the same molecule over here on the left. So anything we do to one, we're going to do the other. So to make those ones on the left look like the twos on the right, I'm going to write a 2 right here, multiply the whole thing by 2, and that's now going to give me 2 H's on the left and 2 Cl's on the left. And now when I compare, that's all I had to do. The Zn's are already balanced. Now the H's are balanced, the Cl's are balanced also. I'm going to go in and just write in ones for the rest of it, so anybody looking at this knows that I didn't just forget to write something. Remember, never write a 0 because that means there's none of it. The whole thing's balanced off. Now we've done this, we spent a lot of time balancing reactions, but what's actually happening in these reactions? We've been putting in these numbers to see what the recipes are, what this stuff's going to look like, but if you stopped and really looked to understand what the atoms are really doing in this, how they're moving around, how they're interacting, how they're changing, how the molecules are changing, we really haven't, but we will now. There's this rule called the law of conservation that says matter and energy can't be created or destroyed. As we saw during balancing, pieces can only be moved around and rearranged, not appear or disappear out of nowhere. And as we saw way back when we learned about heat, things can only get hotter because they absorb energy from somewhere else, not that energy just pops out of nowhere out of thin air. So A plus B equals C, 1 plus 2 equals 3, part plus part equals total of both parts. 1 plus 2 equals 3, not 1 plus 2 equals 4 or 5, or as we saw during balancing, Anna Kendrick. For example, if we have 40 grams of A and we add 20 grams of B to it, how much total grams of C should we get? Should be the same 60 grams. It's just adding the two numbers up. If we have a closed container with 35 grams of liquid water inside and we let it evaporate, how much water vapor is made? Should be the same 35 grams, since the water only changes form. You're not actually creating or destroying anything. You're just moving it from one form to another. And just as we've been seeing when we do the balancing equations, if we had 2 of the magnesiums and 2 of the oxygens, they might rearrange to have each magnesium paired with an oxygen, but it's still the same amount, only the positioning and assortment of these atoms has changed. That's what conservation is. You're starting with the same stuff you're finishing with. It may look different, but it's still the same stuff that's there. We can apply the same ideas to chemical equations. If 103 grams of potassium chlorate on the left breaks down to 62.7 grams of potassium chloride, the KCl, and some oxygen, how much oxygen is actually being made? That's a lot of words trying to get you to do a one-step subtraction. We know what the equation looks like, and we know how much we have of 2 of the 3 parts of the equation. So plug your numbers in and subtract. Plugging these numbers in here, it tells us that if we have 103 grams of KClO3, and it breaks down to 2 parts, one of which is a 62.7 gram sample of KCl, what's the last part going to be? How much is the actual oxygen going to weigh? Plug your numbers in, do 103.0 minus the 62.7, and the remaining piece that's left over has to be the other 40.3 grams, and that's what the oxygen weighs. That's really all you did in balancing. Now you're just doing it with real numbers. Endothermic and exothermic, those are words you know already. I wonder if they'll relate somehow to those 2 weird floaty explosion things that I'm leaving on the screen this early in the slide because they're too much of a hassle to properly animate. Remember from much earlier in the year when we learned that endothermic processes absorb heat or energy? In terms of a reaction, the heat or energy is going into the reaction, so it's absorbed like a reactant and is written on the left side of the arrow. Exothermic processes release heat or energy, so it's coming out of the reaction. It's being made, and the energy term is written on the right side of the arrow as one of the products. So energy going in, left side with the reactants, energy coming out, right side with the products. Different ways you might see this. All right, finally we get past the intro stuff and see some reaction types. What's going on in this picture here? How would you describe this? I'll wait while you look at it and decide. This type of reaction is called synthesis. which means taking two reactants and adding them together to make one product. Look at the picture. It has blue and red spheres combining to make a blue and a red in one molecule. As examples, it's A and B joining to make molecule AB, or iron and sulfur forming iron sulfide. Remember in your bio classes when amino acids are added onto a chain to make proteins? Of course you do. Not at all probably, right? No. But when you do that, it's called protein synthesis. Same thing. Synthesis is just pieces coming together to make a bigger part. Next reaction type, same deal. What do you see happening in this reaction? What's the change that's taking place? Just the opposite of up top, right? This type of reaction is called decomposition. And it's exactly the opposite of synthesis. One molecule is split into two components. The red and blue combo we saw made up in the top example is now broken down to its parts, the separate blue and red spheres. As examples here, we see molecule AB breaking up again into A and B, its separate parts that we started with originally, or table salt and HCl splitting into Na and Cl. So two opposite processes, one you're adding things together, the other you're breaking them down again. Synthesis is Leon Han, sad because they're apart, then finding each other and coming together. Decomposition is, well, the opposite because these things happen. 1 minute you're saving the galaxy, next thing you know, 32 years have passed, and untalented filmmakers bump you off in consecutive movies. It's a shame, but it happens more than you probably realize. Want to hear something really depressing? When I first went to record this, I started to say that 20 years had passed, and I realized that Return of the Jedi came out in 1983, and I clearly still don't have any sense of time, and you likely have no idea what I'm talking about because you're all like 11 years old or something. Who even knows anymore? Reaction type 3. What do you say? Single replacement reactions are when we start with one element by itself, not bonded with any other elements, so in this case the red A, and we react that with a compound of multiple elements, in this case the molecule of blue B and green C. The reaction, the change, is that the single element changes places with one of the elements of the molecule. It gets exchanged, as I said, replaced. The way in which it works is not random, though. The element replaces the part of the molecule it's similar to. So a single metal outside the molecule will replace the metal or positive part of the molecule, and a single nonmetal that's outside the molecule will replace the nonmetal or negative part of the molecule. In these examples, A reacts with compound BC to form A, B, and C. The A replaces the C, so A moves in and C moves out. When zinc and hydrogen sulfide react, zinc combines with sulfur by replacing the hydrogens, which get the boot and leave the molecule to form H2 gas. So zinc replaces the more positive part, the H, not the S. If we're assuming A was a metal, then it will replace C, which might be, actually in this case, it's replacing C, so C would be a nonmetal, A would have to be a nonmetal also. So A would be a more negatively charged thing, B would be positive, C would be negative. It's always replacing the thing it's most like. Last one. If the third reaction type was single replacement, what do you think we call this one? Double replacement is when two compounds rearrange their parts. The positive half of each reactant compound joins up with the negative half of the other reactant compound. I think of this like two couples changing dance partners, and a bunch of the current seniors told me that that's how square dancing works. At least it was at some summer camp they went to. So let's go with that. Double replacement is square dancing. The story also featured people named Lou and Sue, I think, or something like that, and there was some kind of dog, I don't really remember. But just like before, this is not a random swapping of parts, as you can see that each product has both positive and negative pieces. The examples show the general example of this being A and B reacting with C and D to make AD and CB. Well, the actual example is NaCl and AgNO3 reacting with each other. Both parts of each reactant switch places to make new pairs, with now Na and NO3 and Ag going with Cl. The positive part always gets written first in each molecule, each formula, and the negative part then gets written second. So Na is on the left part of its molecule over here, Na is still written on the left part of its molecule over here. NO3 is written on the right part of its molecule here, NO3 is still written on the right part of its molecule over here. And we're barely over 10 minutes because I record these slides out of order, so boo-yah. Single replacement is like if Fred got bored with Wilma and replaced her with Betty. Double replacement is when the two couples switch spouses, which is sad, but the bigger issue here is why is George Jetson in this picture? Where's Barney? And why is the Fred Flintstone on the single replacement picture so roughly drawn? Look how thick those ink lines are. It's like someone drew with one of those twice normal thickness crayons used in preschool. A Mark Rosengarten video about reactions? Why not? But now you know the drill, hopefully. So finish the form. Unless I've told you differently by now, be ready for about 5 questions on this tomorrow. Whichever day tomorrow actually is, since I'm not sure when you'll be assigned this video.